We derive the form of Catalan numbers as 2n choose n minus 2n choose n minus 1, or equivalently 1 over n plus 1 times 2n choose n in the previous video using the reflection method. There are at least two other ways of derivation, one being another type of bijection, the other being an algebraic method, namely the generating function, which we have briefly talked about in the Fibonacci general term video. The first method seeks a natural explanation of the factor 1 over n plus 1 through something called the exceedance. This quantity of a path measures the number of up steps above the diagonal. So in this case, since the number of up steps above the diagonal is 2, the exceedance is 2. Exceedance can only vary from 0 to n, so there are n plus 1 of them. The goal is to find a bijection between paths of a particular exceedance to another exceedance. Then since all exceedances have the same number of paths and there are altogether 2n choose n of them, the number of paths with any exceedance will be 1 over n plus 1 of that, including that of exceedance 0, which is what we are looking for because that means no steps are above the diagonal. But now we want to find the bijection that can make everything work. To achieve the bijection, we use this path to illustrate again. We break this path into 3 parts. This blue middle part is the first step that returns to the red line. Now rearrange these colored parts so that the part after the blue middle step comes before it and vice versa. Now notice that the exceedance of the original yellow path is 2, and after the transformation it goes down by 1. This is always the case because the exceedance contributed by the orange part does not change. But since we put the blue part first, it pushes exactly 1 up step above the diagonal down, so the exceedance goes down by 1. Notice that we can always do everything backward, so we achieve bijection. This method of proof explains the factor 1 over n plus 1 quite naturally as the number of possible exceedances. The next method starts with the relation between the Catalan numbers, expressing Cn in terms of smaller Catalan numbers. To do this, let's summon the grid again. Now, the smaller Catalan numbers mean the number of dike paths from the bottom left to any other points on the red line. The problem is, there are paths that don't touch the red line until the very last moment, so creating a recurrence relation is not as easy as you might think. However, we can first ignore the first and last step, which are universal in all the dike paths, and treat the new path as another dike path not crossing the orange line instead. We can easily calculate the number of such paths to be the n-1th Catalan number. For the other paths, it must touch the red line more than once. It might be tempting to say because of the 2 different paths of the path, the number of any path that has this kind of structure is C3 times C2. However, consider this green path. Should this green path be counted as having a 3 then 2 structure or a 2 then 3 structure? In fact, it is heavily double counted. To avoid this counting disaster, we say that the structure is determined by when the path first touches the red line. So each path should have a unique structure. That means if a path has a 3 then 2 structure, then in the first part, it cannot touch the red line until the very last moment. This is analogous to the logic case we have dealt with by ignoring the first and last step, and the answer is the previous Catalan number. So the number of paths satisfying the 3 then 2 structure is C2 times C2 instead. One final special case is those paths that obey the 1 then 4 structure. But then, we can pretty much ignore the first two steps because there is only one way to achieve this anyway. So, the number of paths adopting this structure is simply C4. Now we can generalize the above procedure to compute Cn. This is equal to Cn-1, which is the number of paths without any structure we mentioned, or those that do not touch the red line until the very last moment. Then add onto it is the product of Cn-2 and C1, which is the number of paths adopting the n-1 then 1 structure, until we get to C1 times Cn-2, which corresponds to the number of paths adopting the 2 then n-2 structure. And finally, we add the last term Cn-1, which corresponds to the 1 then n-1 structure, where we can pretty much ignore the 1 in the structure. We can make this recurrence relation look even nicer. If we define C0 to be 1, then we can rewrite the recurrence relation like this, so that every term is the product of two Catalan numbers. Now consider the generating function of the Catalan numbers, which is the power series with Catalan numbers as coefficients. To use the recurrence relation we have derived, we can consider the generating function squared. To facilitate our calculation, let's produce another copy of f of x for easier reference. To obtain the constant term, we just square the constant term in f of x. To obtain the x term in the square, we can do this type of crossing. And again, to obtain the x squared term, we can do another crossing. We can do this for all the terms of f of x squared. Based on the recurrence relation we have derived earlier, the coefficient of x term is just c2, while that of the x squared term is just c3, and so on. The constant term is 1 anyway, so we can view it as c1. Now multiply x on both sides, and compare this with the original form of f of x. It only misses by a constant term c0, which is defined to be 1. Rearranging, we have this relation that is quadratic in f of x. So by using the quadratic formula, we can solve for f of x. It might be a bit better to move the denominator around, so we can choose whether plus or minus should be used. If x is equal to 0, then the left side is 0, and we substitute x equals 0 on the right side as well. The only possible sign is minus, so we have finished this formula for f of x, although it needs to be defined for x equals 0 in the sense of limits. Now there is one small caveat here, which is that we did rely on the convergence of the generating function, so we need to say that our work is based on having small enough x such that it converges. Essentially, we have established that the generating function equals to the fraction on the left. So if we can somehow turn this into a power series with known coefficients, then we are done. And it can be done using something called the binomial series, which is the generalized version of the binomial theorem. The exact derivation process is not difficult, albeit tedious, so I will not do it step by step here. If you want, there is a link in the description to see this document. But I hope it is clear that this is a special way of deriving the formula for Catalan numbers. The next video will continue the discussion of the banking scenario we have established since the first video in the series. Now notice that we have loosened the constraint that a must be equal to c into just some values of a and c that make sense, that is a being at least c. Give this problem a go and see how far you've got until the next video. If you enjoyed this video, give it a thumbs up and share it. Don't forget to subscribe with notifications on to get notified of new uploads in the series. See you in the next video. Bye!